swangy hands, and this project was actually funded by this company on the left-hand side, K-Water. K-Water is Korea Water, and they are the biggest water resources company in Korea. And essentially, the whole idea was to try to do something that was literally considered impossible. So what this problem was related to this issue. I don't know how many people over here know about the 38th parallel. So the 38th parallel is basically a line of division between North Korea and South Korea. Okay, and North Korea and South Korea were divided around the year 1955. Now, North Korea has no relationship at all with South Korea. It's a very little relationship with the rest of the world. So it's a bit one of those enigma type of countries. And this project was on the request of the South Korean government, who said that people were dying by sudden releases from a large water supply reservoir in North Korea. And essentially, once the water used to get released, it used to be 5 hours at most before which the flood wave used to hit the town. And there was deaths literally every year that were happening. Problem was there was no warning about this release. More than no warning, there was basically no information about what was existing, what data had been collected, how big the dam was, how deep the dam was, what rainfall was in North Korea. So they said, can you help us develop a flood warning system? And the first time this came to me, I said, this is not possible. But then we started working towards it, and I would like to share what exactly we managed to find. So, just another picture about the 38th parallel. This is the parallel with the army in 1955, back over there. This is basically a photo opportunity for the 38th parallel. People go there to get their photographs taken. And probably the most famous photograph is by these two great gentlemen who basically met, and this was the first time American president crossed the line of control into North Korea. And this was at the 38th parallel. So, transboundary water conflicts is really the focus over here. I guess a good example of such conflicts are that information does get shared between many countries like Canada and the US. Okay. In this particular case, information does not get shared at all between North and South Korea. And in this picture, the map of South Korea that you are seeing, the map of the Korean Peninsula, you're actually seeing where the dam is, and you're seeing how close the townships are where you have these people living and who get flooded almost every year because of these sudden water releases. So, how do you solve this problem? We have a dam. We don't know its capacity. We don't know its water level. We don't know the inflows. We don't know the rainfall around the area. We don't know how much water is being released. We don't know what the operating policy is. Okay? So I guess if you have to get started, what would you do? You would like to get some type of methodical estimate of the water levels, the storage. Okay? So using data, DEM data, you can estimate the spillway height, and you can make use of these satellites. These satellites are essentially being used in this particular project quite significantly to do different things. First thing they're trying to do is to get the water level. So basically, water level is coming through altimetry satellites, then optical satellites, where there is cameras sitting up in space, and they're basically taking pictures. But we're using some very intelligent methods because these satellites come with a lot of uncertainty. So we were talking about water quality uncertainty. You take one sample and the uncertainty is huge. What is the solution to that? You take 100 samples, the uncertainty gets lesser. So basically what we have managed to do over here is just to increase the sample size of our samples because the satellites cover everything. And through that, you are able to reduce the uncertainty. Now, after the water level, we need some type of rainfall data. We ended up using essentially, again, rainfall data coming from iMerge through MSWEP. So this is basically reconstructed satellite products. In fact, I was just telling Anu that I have a very good Nepalese PhD student who has you can upload basically a shape file over your catchment, and he uses satellite products that he merges together to give you 1 hour reconstructed rainfall data anywhere in the world. And it's really, really cool. So if you're interested in that, contact me. And this has just been released at AGU last week. This product is really fascinating. The last thing is you need outflows. Outflows are totally a function of dam operating policy. Now, outflows are complicated. We use essentially the SAR imaging as the basis for the outflows. And from this, we derive our operating policy. So number one, water levels. This is a reservoir. Okay, all the Korean reservoirs have this very strange dragon-type, shape file. It's very fascinating but very difficult for a satellite to cover. Now the problem with this is you don't get too much coverage from typical satellites because they don't cross this shape adequately to get enough samples together. So essentially what we do is we use some type of a dynamic water mask. Okay, water mask meaning we are chopping off the areas outside the dam, but we are doing it as a function of the storage height. And we are trying to figure out what is the level at which we are at based on this. And the problem over here is that this particular satellite is, while we are able to improve the approach of sampling using this altitude measuring satellite, by using this dynamic water mask, the satellite still visits once in 29 days. So we are just getting water level once in 29 days. And from these dynamic water masks, we are able to essentially reduce the uncertainty in the estimated elevations. And this is something that is published. This is also at the cost of having very limited data loss using the dynamic water mask approach that we have adopted. Now, this is something that has been published in a paper, and this software is available for people to use. This can be used for any lake system anywhere in the world. The satellite basically keeps on crossing. So this particular software will allow you to download the satellite data for water levels and use the algorithm about the dynamic water mass to derive the water levels from that corresponding data. But the problem is that we don't get too many observations. The amount of observations that we have, they have too many gaps in between. So we need basically some finer level gaps, and essentially that is something that we had to work on using a second approach. So you can see over here, this is the reconstruction of the water level that we are getting, but you can see very large gaps in between. So basically the next issue was, can we use these other satellites to reduce the gaps? And the approach that we adopted was, we realized that satellites have a way of distinguishing between water and land through this variable that they measure called reflectance. So satellite reflectance allows you measurement of water and land, and there is a clearly different pathway for water versus land. But the problem is that this difference changes from reservoir to reservoir, region to region, depends on the depth of the lake, depends on a lot of other factors, depends on the type of shape of the lake. So how exactly can you take this into account and develop an approach to distinguish water and land and use that to infill the water levels? So this is another approach that Pangi had developed. This is something called the dynamic threshold approach, and it's kind of complicated, but basically he's getting multiple water masks together corresponding to different elevations, and then he's generating enough pixels from each water mask. And as a result of that, he's able to basically find a change point. And I know that I'm sort of rushing through over here, but this change point allows you to estimate the altitude, the level of the water fairly accurately, even in very, very small lake systems. I mean, Finding the elevation of a lake in a huge lake like the Great Lakes in America is not that difficult. But these are very narrow, very thin lakes, and this is quite difficult to do. So basically, this is something that is possible to do after this approach. And basically, once we use the STAR or the optical satellites, that 11-day gap was reduced down to 2 to 3 days. So we now have 2 to 3 day frequency time series of lake water levels from the early 1990s up till now. This is another paper that he has published recently, and basically this is in combination with the previous one is probably the best thing that you want. I mean, this gives you the complete lake water level time series anywhere in the world using the satellites that are available for this. Now, the difficult part is finding inflows and outflows, because what we do need is we do need the water levels from those missing days. We are getting the data once every 3 days. We need data in between as well. The only way to get that is to find inflows and outflows. And to estimate that, we have actually done some very interesting work by counting water pixels in a river reach. So I told you about water quality. If you have one sample, massive uncertainty, 100 samples, you have accuracy. What we have done is we have counted all the water pixels in a 10-kilometer stretch of the river, upstream of the dam, downstream of the dam. Okay, this is something that can be done. I have possibly 10,000 samples of reflectance, and this can be used to count how the reflectance is changing from one day to the next day to the next day to the next day. So we are not having stream flow, but we know how many water pixels are covering the surface of the river in the same 10 kilometers day after day after day after day. Now, what do you do with this? Well, what you can do is you can use this to calibrate a hydrologic model. So basically, your hydrologic model is impossible to calibrate using satellite data. But what we have managed to do is we have managed to reduce the uncertainty of the satellite data by covering so many pixels in a defined 10-kilometer range that we have then managed to calibrate some kind of a hydrologic model. So this is some kind of a filtering algorithm that we adopt. And finally, we end up with the final figure, and this gives you your 10-kilometer stretch. Your 10-kilometer stretch then simply counts water pixels. So each day has a certain number of water pixels. So if on average it is 10,000, one day it will be 9,900, another day it will be 12,000. Flood conditions it might be 18,000. You have a time series, use this as a surrogate of stream flow, and this is what you get. So we have this approach called the surrogate runoff model. There's a lot of papers by this very intelligent girl called Hena Yoon, again from Korea. And basically, what this approach does is it says satellite data is not good. But if you need it to be used for calibrating a hydrologic model, you can include some special type of likelihood functions. And through that, you can finally pick up all types of floods that are observed on ground. And this is something coming totally from satellite-based measurements. So the bottom figure that you're having over here is from the model results. Okay, no measured stream flow data has been used in creating this result. So this is papers that have been published in WRR Journal of Hydrology. The software is the one that I have a reference for over here, and this is a very, very powerful approach. Now here in this particular figure, she's using a different satellite surrogate. We have used these 10,000 pixels, the number of pixels in the river in a 10-kilometer range, as the surrogate, and then calibrated a hydrologic model. Now, I will not get into which hydrologic model is to be used, because I personally believe all hydrologic models are equally bad or equally good, depending on what you want to call it. Okay, it all comes down to the data. We have data, surrogate data, not direct stream flow data. We have surrogate data, but now we are in a position to estimate flows in these rivers where we have no possibility of getting enough data. So now, coming back to the North Korean, South Korean problem. Essentially, we have inflows into the dam. Okay, we have water levels. Okay, no gaps. everything has been infilled, okay? And we have outflows as well, because we use the 10-kilometer stretch, okay, downstream of the dam. The downstream of the dam, you cannot use a hydrologic model. You have to directly count the satellite-based outflows. Now, the rest of the problem is very straightforward. You just have to figure out what the Koreans are doing in terms of the reservoir operating policy. So, what operating policies to basically consider was a big issue. But to get these three figures, I need to emphasize that no ground observations were used. The only thing that was used was data in South Korea, okay, after it has been released. And basically, we checked using that whether the approach was actually making sense. So finally, the last part is we assumed a reservoir operating policy based on advice that we got on the typical reservoir operating policies that were being used in China. North Korea is very close to China politically. Basically, they were using that operating policy. And we had some fancy multi-objective function that was used to optimize that policy. But the end result was this. These are actual releases and model releases. These model releases are coming from satellite rainfall, a model, okay? No new satellite observations. So all we are using is satellite rainfall. So basically, if you have your satellite rainfall, maybe 9-10 hours before, okay, the actual water release, you are able to get that type of accuracy in terms of your water release. Now, you might ask, what is the danger in this? The danger in this is that the operating policy might change. The Koreans might decide that they want to release water in, low flow conditions or low water storage conditions, etc. But if that does not happen, if the past is a surrogate of the future, then I think we started with an impossible problem, and we have kind of managed to basically provide a very decent flood warning system for South Korea with at least a 9-hour lead time with no ground data whatsoever. So that's basically all that I wanted to say. Thank you.
Any quick questions, please? Yeah. Okay. Yeah.
I'm audible. I think I can start.
Yes. Okay.
Thank you very much. This was a very exciting and very interesting presentation business made. Especially, you address the data sharing issue because the North Korea was not sharing any data with South Korea. So my question is, can the SWOT just talking about the SWOT question program is that like could be adding some value to your research, or are you planning to use it because it also keeps on I don't know the size of the width of the rivers or the dam, but if you can provide that thing. So one question is that, and the second thing is it like transferable to other regions as well?
Yeah. This is a PhD project. So PhD project cannot be location specific. So basically it has to be applicable globally. All the software that I've said can be run anywhere in the world. It's just for illustration that we have used this particular problem. We have a second project in Fiji. So the Fijian government basically wanted a water quality measurements in a river where they had no monitoring. And we gave them the same thing that was funded by New Zealand aid. Same methodology, but here the model is not a hydrology model, it's a water quality model. So essentially something like a SWOT that is being calibrated using satellite-based surrogate stream flow. Same 10-kilometer length, using that as a surrogate of the flow, and we are calibrating it. Regarding SWOT, the SWOT people have been after us. They have basically wanted this technology, and we've had a lot of discussions with them. Their algorithms are different to us. Okay, our algorithms are very much developed for very narrow winding rivers. In Korea, you don't have very wide straight rivers like the Ganges. Okay, Ganges is relatively easy for a satellite to observe something from. But the narrow winding rivers, it gets very, very tricky because they change their path, everything goes crazy in that. So basically for that type of conditions, SWOT what has limitations. You will get some answers, but the accuracy of this thing that we finally have is scary. It's like, NSC is a 0.96, okay, and daily water level time series are being measured. So it is very, very, yeah.
I think we can collaborate because we are using a SWOT satellite data and we're trying to validate those which are measuring some rivers, 7 rivers in Nepal. India transformed the rivers, and we were trying to use them, but looks like that there is some tricky, and as you said, it needs to be flat and very wide rivers, and the rivers in Nepal, Himalayas also, and that same kind of situation. So maybe that can be done. So I'm looking forward to meeting. Thank you very much.
Sir, one question. As per international law, we must have only international boundary information requires to be shared.
Yeah.
North Korea does not mean that.
I think, yes, you're right. Laws require a lot of things, but it doesn't always happen. So, the Mekong is the same thing. Okay, Mekong is
There might be some river which may be even of the same of North Korea. Different situation happens.
Yeah.
North Korea, what he will do, what the country will do.
Look, I cannot comment on politics and government, but if you speak to a Bangladeshi person, they say India doesn't share information and people lose lives over there. So it's all a little bit complicated. But basically, the whole issue over here is governance is a problem. I personally, my belief is, if basically data was available on a mobile phone to everyone in the world.
That's okay, I think. One last question, yeah?
Thank you, sir, for this nice presentation. So I have a question. How do seasonal change and cloud cover change for this particular accuracy of dam monitoring for these actual issues?
Very, very good question. Optical satellites have a problem with cloud cover. Okay? So when optical satellites come along and there is significant cloud, then that creates a problem, and that creates data gaps. But the data gaps don't matter because you're using this data as a surrogate of stream flow, not directly. You're using it to calibrate your model. So you're calibrating the model's parameters, you're updating the model's parameters. Finally, once you have the model, the satellite doesn't matter. All you need is rainfall. If you have rainfall, you can produce anything. So we are using the satellite simply as the basis of creating the digital twin that Anu was talking about. So we basically have a digital twin, but we have created that twin with no data on ground. That is the beauty.
Thank you, sir.
So thanks, I think we round our class to assist.
Our next keynote speaker is Dr. Manoj P. Samble. He is a leading Indian water resource scientist and the Executive Director of Center for Water Resources Development and Management, or CWRDM, Kozhikode, a premier research development training and consultancy institution in water resources and under the Kerala State Council for Science, Technology and Environment, based in Kerala. He has been serving as the Executive Director of CWRDM since March 2021. Dr. Samble's work focuses on sustainable water resources management, hydrology, rainwater harvesting, groundwater recharge, and climate resilient water systems, among other areas in the water sector. Under his leadership, CWRDM conducts research, capacity building, and policy support for efficient water management and disaster mitigation, and collaborates with government, academic, and community stakeholders. He has a strong academic research background with numerous publications and projects in water science and management, and contributes to national and international discourses on water sustainability. May I invite Dr. Manoj P. Samble for his keynote address.
Respected Chair, Professor VP Singh, other dignitaries, my dear friends. First of all, I thank the organizers for giving me such an opportunity to present before the galaxy of very senior experts across the globe. Uh, I'm from a very small regional institute called Center for Water Resources Development and Management in Kerala. Basically, I'm a scientist in Indian Council of Agricultural Research for last 30 years. So that in my presentation, I will be discussing something about the learnings which I had from ICR as well as from CWR and from for last couple of years. Basically, these are the challenges and focal areas whether we are in Kerala or in Bihar or in Chhattisgarh or in Assam or somewhere elsewhere in the globe. These challenges are more or less common. Climate change impact, recurring floods and droughts, increasing emission of greenhouse gases, water security, quality and equity. Equity is a big issue. Then changes in water use and land use patterns, fragile ecosystems, river management, environmental issues. And last two are basically not challenges, they are rather opportunities. In agriculture, basically I am an agriculture scientist, so that in agriculture, like Dr. Singh and many speakers are telling, around 70 to 80% of the water in India is being used in agriculture sector, agriculture water management. So that how best we can manage water for irrigation in agriculture sector, and how we can use the latest platforms like AI, IoT and other systems, digital tools and all these things for better management of water, especially in agriculture systems. And climate change we discuss a lot, but one thing we many times we forget is how the climate change apart from the direct impact like droughts and landslides and floods, how it is affecting us in terms of our public health, labor, livelihood, and fisheries, agriculture. Agriculture, one of the studies says that if the temperature goes up to 2 degrees centigrade, then the corresponding decrease in wheat production is almost 0.75 per hectare. It's an IRS study. It's a huge number, right? And again, livelihood in India, as per Lancet study, 191 billion potential labor hours were lost due to heat exposure in 2022. This is one of the analysis in my state in Kerala. Though we know around 3,000 millimeters we are getting annual average rainfall, but the rainfall distribution is very much skewed. You can see the southern part of Kerala, like the Tiruvandhuram, Kollam, these districts are getting comparatively less rainfall, but that is well distributed. But if you go to southern part, near the Mangalore, Kasaragod districts, we are getting more rainfall, but it is more skewed. So that more drought incidents are happening in the northern part of Kerala. And again, you can see one interesting thing in the circle. There are two places in my district where I work. It is Kozhikode district, Calicut. You might have heard IIT Calicut and NIT Calicut. There are two places. One is Vanagara and Koilandi. The road distance is hardly 30 kilometers. But you can see one of the seasons, the anomaly in rainfall. One place it is plus 100%, other place one place it is plus 300%, other place it was minus 100%. So that the distribution of rainfall is so erratic, so unpredictable these days. And heavy extreme rainfall events are more common. Cloudbursts are common. And again, you can see 44 rivers we have in Kerala, but the changes in river flow, the minimum flow and maximum flow difference is so huge in most of the rivers. And again, if you come back to India, we know the statistics. I don't spend much. I don't want to speak more about that. But one thing in the circle you can see comparison of three countries. One is Israel, one is India, and another is China. That is agriculture GDP per cubic meter of freshwater withdrawn for agriculture. In Israel it is 4, India it is 0.4, China it is 1. That's the meaning. What is the meaning? With the same amount of water, Israel is producing 10 times more food grain, pulses, vegetables, fruits, cereals compared to India. Our water productivity is less, our irrigation efficiency is less. So that how best we can increase this. Again, groundwater is another problem. As per UNESCO's report, the total groundwater extraction by both America and China is only 25%. India's groundwater extraction is 25% only being extracted by these two countries together. And again, we have to bring more area under irrigation. If we increase irrigation by 1%, the corresponding increase in greenhouse gas emission is 2%. More depth we have to lift water, more fuel we have to burn. So that again, possibility is to increase the irrigation efficiency, so that we can reduce increase irrigation efficiency by 1%. Corresponding decrease in greenhouse gas emission is almost 20%. And again, coming to wetlands, wetland is a major discussions today. So that wetlands in Kerala, if you come, you can see hundreds of wetlands. These are 4,500 wetlands, 4,500 wetlands in my small state. Across India, we have different wetlands, marine wetlands, we have inland wetlands. Wetlands are useful for water security, flood control, biodiversity, bird sports, livelihood and tourism, climate change control,
and urban resilience and many things. You can see many examples also here. But most of these wetlands are subject to different types of issues. You can see the the chart which is given here. Different types of wetlands, the inland wetlands, the marine wetlands, the impact of climate change, impact of habitats, impact of anthropogenic activities, how it is affecting, how serious it is, and what is the trend towards the future. These are given in this slide. And finally, we speak about the climate mitigation, adaptation, and resilience, and we have lot of opportunities. But the thing is that we should not take all the things together. Rather, we have to analyze what is the specific issue with respect to the microclimate, with respect to the land use problems in my area, and accordingly we can select the package of practice which is suitable for our area. And finally, we can use the AI and IoT techniques and with all of the digital systems available presently. And basically, we will now discuss a few challenges, especially in the field level, about agriculture water management. One is, of course, the disruption in the weather pattern. The second is less water use efficiency and water productivity, I have already told. Then third one is very important, community engagement. Unless otherwise the community is taken into consideration, the participatory irrigation management is not taken care of, we are not going to achieve water productivity. Again, another big problem is in India. In one of the previous slides I have shown, actually I didn't explain about that. The total water demand in India is going to be around 1400 or 1450 by 2050. And our total supply is only 1123 billion cubic meters. So that from there the extra water will come. We can either increase the supply, maybe rainwater harvesting, groundwater research up to some extent, but we can increase supply in a big extent by reusing the grey water. So that how best we can reuse grey water, especially for agricultural water management, is the question before us. So that we have to think seriously about that. And again, we have to think about the residual effect and how best this water is for the different types of crops. All these experiments we have to do. Now, personally, we are doing one project with INCGW, and we are testing how this grey water can be recirculated after some basic treatment for irrigation purposes. Then again, pollution is another issue. Lack of adaptation of new ideas and technologies for irrigation planning, and lack of technology hiring center. That is, again, we are developing a lot of technology. We are creating a lot of knowledge. How this technology or knowledge can be translated to some viable opportunities for the farmers. How they will get this technology. We have KVKs in all the districts in India. And apart from that, how best we can do this, because KVKs are basically focused on the agriculture science part, the crop, the pest and disease management. But the agriculture engineering or hydrological engineering or water resource engineering has to be considered more seriously by Krishi Vigyan Kendras and other related systems, extension systems. Then again, lack of pilots and replicable models, especially climate smart villages, carbon neutral villages. These concepts, at least once in a district or once in a taluka, we have to seriously think about. Then policy level, we have a lot of issues. One of our participants was continuously advocating for data pooling and data sharing. That's a big issue. Data is sitting different places. How we can pool it, compile it, how we can distribute it in a proper, how we can put it in a common platform, open source. Again, use of software, digital tools, platforms are limited for academic purposes only. Even in India, this is the thing. Even now, it is happening. Everything is happening in the academic level. But how we can penetrate to the field level engineers and officers? How the technology dissemination has to happen? How this can be translated to a viable commercial product or a usable product, which really all the stakeholders can be used. We are speaking about a lot of models. How this model can be translated to a graphical use of interface or a mobile app, so that ordinary people can do. I will show some examples in the coming slides. Then digitalization challenges for agriculture water management, data access, affordability and reliability. Chances of misinformation and data manipulation, that's a big issue in our country. The lack of field testing, ground truthing, validation and bias correction. Dynamic nature of climate changes, land use, land planning, then water supply, demand, etc. Then non-availability of free or cheap or affordable satellite or meteorological data. Then less open source or indigenous software, data system, decision support system, expert system, etc. And finally, so most importantly, we have a lot of inertia to migrate from traditional system to digital data-driven systems. So that we have to somewhere, you know, push the people, all the stakeholders, slowly. May not be immediately it will happen, but slowly the things have to happen. And I'm very happy that nowadays things are changing in a better way. And this is, you know, Wetland is one of the beautiful lakes in Kerala. If you can go to those places, Alapi is houseboats. But this Wetland is a place where we have a lot of issues with respect to water quantity, water quality. There are a lot of conflicts with farmers, fishers, and all the stakeholders. So that what we have done, we have analyzed all the problems and we categorized into three categories. One is natural problems, and the second one is partially natural, partially anthropogenic, then purely anthropogenic. Then in some of the problems, policy level interventions are required. Then accordingly, IMP, Integrated Management Plan, is developed for the lake with the support of Wetland International South Asia, and we have given it to State Wetland Authority. And there will be, and we have developed, we have divided the entire lake into different grids. I will be showing one of the slides in the future. So wherever this water, when we are thinking about water resource management, 6 things are very important: demand, supply, water governance and policy, capacity building, disaster management, and climate resilience. And after that, the blue box is basically the local issues, the micro issues that you have to see. It may be different from Lokpak, it may be different from Lokpak to Wetland to Pushkar. So that accordingly you have to find out whether lake or your catchment or your command area or your watershed area is concerned. The local issues you have to see, and finally you have to see how you can do the organizational innovations, what all of the innovations you can bring in terms of policies, rules, organization, how you can improve the participation, what are the new technologies you can introduce or you have to develop, and in the most importantly the dissemination part, the expression, and again another most important part is economics, how you can converge and pool the resources for different activities. And now in coming slides, I will show some of the examples where we intervene. One is water budgeting. Water budgeting is nothing but it's a report. On the left side, we are calculating the supply of water from different sources: surface water, groundwater, export and import. On the other side, the water demand for different sectors. And one important thing is we are not calculating for the entire year only once. Rather, we divided each month into 3 segments of 10 days each, and totally we have 36 segments in a year of 365 days. And for each segment, what is the water supply and what is the demand for different sectors. And this we have completed in around 700 gram panchayats in Kerala. We have around 1,200 gram panchayats. We have completed for 700 gram panchayats so far. And I'm very happy to inform you that the NITI has taken up our methodology which we developed, and they also developed the water budgeting protocol. It is released on 19 November, and for 25 aspirational blocks in India, now they are going to introduce this water budgeting concept. And again, the framework which is for the catchment for the agricultural water management, we all know. So basically, we will do some climate modeling. We will find out what is the runoff. Then accordingly, we will divide for off-farm economic purposes, then off-farm e-flow purposes. Then we will come to the on-farm. On-farm we have conductive use, both groundwater and surface water. Then rainwater harvesting. Everything is based on the crop agronomy, the ET or the finding out the water requirement of the crop. And adaptation options, we can do a lot of things to the departments. We can suggest so many things, but again, everything depends upon the local issues. Whatever the adaptation measures you are going to take, you can take a combination, you can take individually or collectively, and take the combination and implement in our area, in your area, as per the requirement. And again, digital agriculture, we are practicing a lot. We are trying to practice a lot. Some of the examples I will be showing. Now everything is available in the fingertips. We have a lot of sensors available, a lot of systems available in the field even. So there are 2 examples. One is Gramwork. This based in Bangalore. I'm one of the advisors of that company. This is basically ET-based irrigation scheduling. They have many services. One of the services is ET-based. So that what is the exact requirement of water for a crop at a particular soil at a particular time can be measured on real time, and accordingly water can be supplied. So that if you subscribe with services, their team will come and install an automatic weather station in your place, and they developed the algorithm based on the Feynman-Mondius equation and many other codes they have developed. They are also measuring the soil moisture data. So everything will come together into that algorithm, and algorithm will decide what is the exact amount of water the crop requires. Then accordingly it can be given, and we validated it. It is working well, and now we have almost 5,000 customers across India. And 2023, Wakeful Foods, they have acquired Gramworks for an amount of $2 million. And another one is another friend from he was my junior at Canada, and he started a company called Ubaj. Basically, if you go take his mobile app and enable the latch launch, it will capture the soil nutrient status. What is the NPK? Because the soil starts given to all the agriculture fields in India, so that we have some records. But the library is not available. It is all are isolated, sitting somewhere. He has collected, but he made it for Punjab and Haryana first. He is based in Mohali. So if you go any places, enable the latch launch, it will capture the NPK status. And he also will take some hyperspectral image support, and in a large area he can measure what is the where the nutrient deficiency is there, where pest attack is happening, where insect attack is happening. Accordingly, he can take necessary intervention. And he started thinking about agriculture drones way back in 2016 itself. That time, Government of India has not started a policy on agriculture drones. Now agriculture drone is very common in the policy matters as well. Another one from Maharashtra, one of the farmers, he approached us, his name is Vijay Gabde. He developed a mobile app for finding out the depth of water in a borewell. Very difficult to find out the depth of water in a borewell. So that if you take a mobile phone, a smartphone, go to, after of course installing this mobile app, go to the borewell, tap on the metallic cap of the borewell, and he will just measure how much time the sound wave took, go down and test the water table and came back, and accordingly we can find out the depth of water table. And we tested almost 500 borewells in different parts of Tamil Nadu and Kerala, and we found it almost 99% accurate. And different softwares we developed. Another one interesting work we are doing is basically hyperspectral images we are using to find out the soil nutrient status. As we know, the soil nutrient status is generally measured by descriptive analysis. You have to take a soil sample, do the testing, and it will take a lot of time as well. But here, if you develop a spectral library of different NPK combinations, basically NPK are the three major elements in the soil, so that if you go any places, you can develop a signature, and that signature can be matched to the things in the library, and so that you can at least find out what is the nearby NPK status or the relative NPK status of the soil, so that in a short time, in a big area, you can find out the nutrient status, maybe in a less precise state. Another work we are working with the DST now with the native source AI-based landslide prediction system. Again, we are using the proof of concept project. We are using three sensors: soil accelerometer we are using pore pressure sensor and soil moisture sensor. We are using a camera, and so that everything will go to the algorithm, so that we will get some information about a possible landslide at least a few hours before, so that at least the evacuation can be happen. We cannot sometimes sell the property, but at least we can sell the life. It is based on the Wetland landslide. After Wetland landslide, we supported and DST supported us. And another few softwares we developed basically for decision support system. And the thing is that all the softwares have to go to the farmers. Otherwise, all these things will go waste. Another interesting software recently we developed is we got a copyright also. Water citizen assessment tool we call Water Cat. Basically, in a stream, some of the areas may be highly polluted. We can say it's sports, maybe in a lake. So that what we have done, we have told in Calicut city we have a stream called Canoli Canal. Canoli is a British lord. He constructed this canal before the independence. So this canal, many places there are a lot of waste is getting dumped, a lot of sewage is getting added. So that we 36 points we have noted, and we mobilized some of the school and college students. So we gave some water testing kits to them, and it is connected to a satellite imagery on real-time basis. So they are going to the places on constant intervals, collecting water samples, doing the water testing, and putting it into the mobile app, and everything is actually getting loaded to the satellite image, so that the district administrator, the mayor of the city, or the collector can see which one of the part of the water body is getting polluted and what is the water status. So that we still now it is working, and our district administrators are using. Actually, this part of the water for change project by NWO Netherlands. IIT Roorkee was also part of it. Kansal was our partner in that. And another one is water forks, that is again the community-oriented water management program. Again, another one which is connected to this is carbon mapping. We are speaking a lot about that, but we should not stop only in water, but again, this everything is connected to the natural resources management. So that carbon mapping, we developed two frameworks. One is especially for mapping carbon in the agricultural field, and both are published in current science as an approach paper, So that action plan for rivers and lakes. So that whenever we think about any lake, there are three factors we have to consider. One is the water spread area, second is the wetland area without blue water, and of course the catchment. So that we have to see the issues with respect to each area, then develop the strategy. And basic strategies include, of course, now I have 3 slides left, spatio-temporal water availability in the basin, then impacts on climate and anthropogenic changes. Then again, an information system is very important, whether it is wetland, whether it is any sort of water-related system or natural system, we should have an information system. So that in Karnataka and Kerala, we have KWR, Kerala Water Resource Information System. Karnataka Water Resource Information System is much better. If you can go and see what are the water resources, what is their current status, what is the amount of water available in different, surface water sources, what is the groundwater available, and it can be connected to Jal Jeevan Mission, JJM website also. That is also a very dynamic and interactive platform. So that this water resource information system should be available in the public domain, so that people can take decisions. They can also give the input. So that wetland information system in Kerala, we called it VIAMS, Wetland Information and Management System. It's an open source platform, so people can access it, they can get the data, and they can also register their name, and they can give the input data as well. Then again, studies on hydrological alterations, environmental flow, flood mapping, pollution, sand auditing, and so many other things come. Then finally, the IWRM plan is very important. Integrated water resources management plan is required. Flood forecasting, early warning systems, water budgeting is important, I told already, and everything. Again, another interventions like pollution control, sustainable land use, stakeholder engagement. We are discussing these things very regularly. And wetland management is concerned, again, two words are: one is the participatory governance, of course, the local ownership, and the ecosystem-based approach. These two are participation and ecosystem-based are two important things to be considered when we are thinking about wetland management. So that again, 5 items here. One is institutional reforms and legal framework, very important. Capacity building of all stakeholders. Now, Amrit Sarovar and Amrit Sarovar programs are there, so that we have some issues, some programs like Wetland Mitras, how the local stakeholders can be mobilized, they can be incentivized, so that they will be part of the wetland conservation program. Co-management and citizen engagement, I already told. Then science and technology, how the science and technology, our platforms, CES and other platforms can be integrated and used in a proper fashion. Then integrated wetland management plans and its alignment with the national programs. Already so many discussions happened in the morning session. And finally, this is the final slide, the policy level interventions. Already I told this the conclusion and compiled way of presenting the things. Better regulatory policy and governance, very important. Micro level climate monitoring system. Now, recently, Panchayat election happened in Maharashtra, Kerala, Goa, Punjab, and many places. So one of the things we have to sensitize the local bodies, the local Panchayat Raj institution is to install a small automatic weather station if possible, at least once in a taluka. So we will get micro level information system. Now we are developing flood forecasting, early warning, drought management system based on some data some years back. Very, maybe a district we have only one data, and we are using that data to predict something, so that it is so inaccurate. It is not at all precise. So we should have micro-level climate monitoring systems, water efficient practices like AWD, and many things we can think about. Early climate warning disaster management system, water resource information systems, already told. Better integration of the convergence is important. Financial inclusion, capacity building, empowerment, extension, advisory services, we already told, local level planning and community engagement, and of course the technology use. That we are responsible. Where the technology, what is the appropriate technology is very important. Appropriate technology has to be identified and it has to be disseminated in a proper fashion which they can also understand. Knowledge creation and dissemination is very important. Thank you very much.
Any quick questions, please?
Sir, how to conserve water and soil in Kerala due to rubber plants and other because the water level depletion due to rubber plants and sustainable environment in Kerala nowadays.
Yeah, actually, rubber plant as such may not create any problem, but the problem is many places in rubber plantation, the forest is destroyed. It is done in the hilly areas. So in the hilly areas, without proper soil and water conservation measures, many places the plantations have been done. So it is creating issues. But now the rubber board, if you need subsidy, you have to adopt soil and water conservation measures. So after that only they will be giving some subsidy or some registration for that. So nowadays, I think rubber plantations are not that much harmful. Previously, what we are expecting, but otherwise, it's not a big problem. But in some of the areas, in the hills, without any this SWC, soil and water conservation practices, they are cultivating, they are doing the plantation. That may be creating issues.
It affects coconut planting and other reason why.
No, actually, rubber plantations are mostly in the high range areas.
Okay.
Coconut may not be mostly in suitable for them. Coconut is mostly in the coastal area as well as in the midland area. This is more than 7.5 meters MSL.
So if there are no questions, thank you very much.
Thank you, sir. Our next keynote speaker is Professor C.S.P. Ojha from IIT Roorkee. So, Professor Chandrasekhar Prasad Ojha is a distinguished Indian academician and Institute Chair Professor in the Department of Civil Engineering at the Indian Institute of Technology, Roorkee.
That's okay.
He earned his PhD in Environmental Hydraulics from Imperial College, University of London, and has been a faculty member at IIT Roorkee since 1980. Becoming a full professor in 2004, his research expertise spans surface and groundwater hydrology, environmental and fluvial hydraulics, and water resources planning and management, with a strong focus on climate change impacts on water systems. Professor Ojha has co-authored several influential books, published extensively in reputed journals, and supervised more than 50 PhD students. He served as head of Civil Engineering Department from 2015 to 19 and holds international appointments, including as adjunct professor at the University of Missouri. He is also a fellow at the American Society of Civil Engineers. I now invite Professor Ojha for his keynote address.
So good evening, everyone. We are running very late, I know. Thank you for your presence. This is the some work on the river Kali. The reason for choosing this topic was that Dr. Ramakar Jha, did his PhD work on this river, and he looked into water quality and flow simulations in river Kali. Prior to that, one of other PhD students, Professor M.C. Ghosh, he retired now. He also worked on river Kali. And whatever the measurement of BOD and other water quality parameters they took at that time, he did the experiment in 2005, around 2005, goes around 1995, and I was looking into the data of river Kali in 2025, nothing has happened. This is the issue of here. Now, Why it is so? So on 6th November, I think Cabinet Secretary Home Affairs, invited me also, to have some discussion regarding the quality of Jamuna river water. And Hindan, the Professor Tarek's favorite river, meets Jamuna, and my Kali river meets Hindan. So, if the Jamuna water quality is poor, Hindan water quality is poor, maybe someone can say that because of Kali river. I don't know. Okay. So with this, I thought we should do some real work in the river Kali, and there was also emphasized that I will try to do some meaningful work simply by doing some research. We just can't gain much, right? So this is the background of this today's topic, something about river Kali, and then we are also doing some work in collaboration with the Indian scientists at National Institute of Hydrology, right? So currently we have a project also, and if you try to look on the work done by scientists at NIS, they have their own constructed wetland, and they try to demonstrate that they can treat the wastewater which is generated from the NIS colony, and they have done successfully that. So it works well. The only problem is that the level of nitrate and phosphorus is high, and when they try to use this water to irrigate, farms and all these things, the grass, germinate very quickly because it gets nitrate and phosphorus. So they have to spend some money in cutting that grass, right? So that's the only problem they have. But anyway, so this can be used. Coming back to the river Kali, you can see a lot of things here. Nothing pleasant to show except that someone is traveling by a buffalo or walking around the river, and how he is exposed into the Kali river, and now what are the health hazards you can anticipate. Okay, whatever the time you spent in the river. And few more pictures of river Kali. The name indicates that river is really polluted. Okay, and sometimes also there is discontinuity of flow. Okay. When the PhD work was done, it was the time when the river was full, right? But now this is the kind of situation it gets, right? Lot of industries, sugar industries are located along this river, 6 sugar industries, and they must be treating their wastewater. I don't know to what extent, but still the situation remains same. So there is no change in that. Okay. Okay. So with these few pictures, some background on this wetland is there, which I have not skipped this because all of us now know after this day's lecture that what are wetlands, what is Ramsar Convention, what are different classifications of wetlands. I'm not going into details of all those, so I will just skip this for the time being. But what is interesting is that lot of treatment process, can take place. Now, few years back, I think prior to Corona period, I visited China and there we supervised a project on constructed wetlands. The focus was primarily to treat the runoff generated from the, storm runoff, right? And so that paper is published and available. You can look into the performance of those constructed wetlands. Again, this really helps. Okay. So with this idea that this wetland could be useful, so we try to look into that, how to decide the surface area of a wetland. Okay. And this is the approach used by our colleagues at NIH, right? Looking into the complexity of water flow when it takes place through a wetland. You just cannot say that it's complete, it is reactor or mixed reactor, it's a hybrid class of hybrid thing, a lot of things are there on the way. So we just cannot use a very simple expression. The way it is done, it can be useful if you are just doing this some pilot plant study or something like that. There obviously you can use such equations, but when you are dealing with the real design of the wetland, then you have to really go for the classical hydraulics, see how the flow is taking place, where the velocities are attenuated, so, and where you can assume that the classical, this straight line reactor junction is useful. So you can look into the finer details of this one. In terms of the treatment also, somewhere the roots are there, right? And how the root uptake is taking place. So all these things have to be seen very carefully before you figure out that what is going to be the effect policy. So still those who are trying to do research work in the wetland area, wetland, I think they have to really look into very carefully. And this simple expression may not really work out everywhere. So I think this is what I wanted to emphasize here. Okay. So we picked up two villages in this Kali River catchment, and the idea was that we should go visit these places and try to propose some design and try to consult the local people and Gram Pradhan, the village chief, right, to see that how improvement can start from the village level. That is the goal. Because I do not want that after a few years again, if somebody reports the same water quality in the Kali River remains, then the purpose of doing this in outside. So I think I have started with that vision that now we will visit and then we will try to have the actual implementation of constructed wetlands, try to do some experiments, see what kind of improvement does it provide to River Kali. So that's the goal of this one. Now, the basic concern is when we try to do these computations, I think the area requirement also comes out to be very high because we are not doing any treatment. So it is very important that such a huge area may not be available at the village level, right? So we should also then have the options available with us. Then what are you going to do if that much area is not available? So I think I will also, share some of this work which we are currently doing in collaboration with the scientists at NIH. Okay, there are hydrologic simulations here. So we have done all these basic studies, and then we have come out with this area computation, which turns out to be very large. Okay, so I think this is the kind of work, and see the area requirement. In the last column you can see surface area requirement in the last column. So this much area may not be available. So we need to reduce this load which comes into the wetland. So that is the key concern. Which we are going to with this proposal with any village level, and we say that you need this much area to and you should provide some space so that we can think of constructing some wetland that may or may not really work, right? So I think this is where we are right now. And again, another problem, I visited the site few days back. I think I gave this presentation in Varanasi also on the restoration of river health Kali. And see, another problem is now you are getting huge amount of plastics in the river Kali, right? Unbelievable. When this work started, when Dr. Jha was doing his PhD work, I think there were no such problems. Now this is another dimension which has been added to this river Kali, that we are getting huge amounts of plastic, right? And they are trying to remove the plastic manually. So all these kinds of problems are there. So I think with this I just wanted to say thank you, and I will take some time, just 2 minutes more because I know, and I just wanted to keep it brief. So yeah, the other one, yeah. Just wanted to show some of the work which we are doing with the NIH scientists. So there is a project is sponsored by Very High Development Corporation, and what I am trying to highlight here is, I will skip the general slides, right, and just come to the work which we are doing right now. Okay, so again, wetland feature here, no problem. So this is a kind of, you see this is sponge here, right? The left hand side. So you are having a sponge type of thing here. Even you can use these bottles, just chop it, make perforations in this, try to put a sponge in this, a layer of sponge, some gas, layer of sponge, connect it through a rope, right? You will have such system, okay? Anyone can have it, such systems in the home also, okay? If you don't have these bottles, you can use this plastic cup, you put a sponge, you can just put a thread there, you can just use it. Now, this is what is being done here. So this is the, we are also collaborating with the Japanese scientists here. So they just try to put it. And the advantage is that once the biofilm growth develops over these sponge, this really works wonder. See in these columns how they are stacked, and how the flow is coming out. So just stack this, okay, with the rope. That's it. And then you can see that to what extent the removal takes place. Removal of BOD, COD, everything. It really is working very well. So based on this, you can see few more photographs here. We have actually set up this small scale plant, okay, and we are treating the wastewater which is generated from the NIS colony, part of the NIS colony, and this is really working well. So just an idea that if you can implement this, right, in combination with what we are proposing, that we are going to have this much area of the wetland, and if perhaps you can reduce the load of the influent by using this technology also, the combination of the two may be certainly going to be helpful in reducing the wetland area. That is the goal. So our next step is to go for this one, few more photographs, okay, and see the clarity of water, the influent water and the DHS in the last, okay. See, this is the kind of improvement you are getting. You can see the color, it is certainly acceptable. The kind of removal is also very increasing, BOD value 10 milligram per liter. So this is the technology which we are thinking to integrate when we are going to really convince the farmer or village level persons that you also implement it and then combine with this wetland so that your overall land requirement also reduces. This is what Professor Tare was also emphasizing. We have to go for hybrid approaches, right? So I think this is some work, which we are still doing, and you can see few more views. Then how we are testing it, and I think then we can certainly have a better future. We can really think of rejuvenating the river Kali. Okay, so I think with this I would like to conclude here. Some more results are there indicating that this system is working really well. But then we have to see other aspects also. So I think with this I would like to conclude here. Thank you very much. Okay. Yeah. अरे मैं वहीं आता हूँ
Thank you very much, sir, for your wonderful presentation.
कुछ काम फिर आप ही काम लगाएंगे आप आइए तो लगाते हैं वहाँ पे काम करेगा.
So I think we are running a little short of time, and we have maybe 9 presentations. So and at 6 o'clock, I don't want to miss that any of you should miss the cultural event. And now our cultural team is already here. They're properly dressed. You can see them. They have come just now. So maybe we can have 1 or 2 presentations, and then we can wind up. So I think one is Nehal Londe Madam has said that she wants to make presentation. Anybody else who volunteers to make presentation? You want to make a brief presentation? Okay. And anybody? You also want to make a presentation? Okay. So we can have very small brief presentations. Professor M.K. Verma, first you come, then you come. Very old. When I started in the morning, very old, so logo ko laga very old friend. Okay. Right. Yes, please. शॉर्ट में कर लें हम लोग कल्चरल को भी थोड़ा सा वो आ गए हमारे आर्टिस्ट दिख रहे हैं. Cultural is very good class.
Our next keynote speaker is Professor Dr. M.K. Verma. He is an experienced academic leader and engineer who served as the Vice Chancellor of Chhattisgarh Swami Vivekananda Technical University or CSVTU in July, where he led efforts to enhance technical education, research and institutional quality in the state of Chhattisgarh. With over 3 decades of experience in teaching, research and administration, he has previously held senior academic roles including Dean and Professor, and has been recognized with awards such as Young Scientist Award and Shiksha, Shiksha Ratan Shiksha Ratan Trutta for his contributions to engineering and technical education. Under his leadership, the university pursued academic reforms, industry collaboration, and strengthened its research culture. Sir, may I invite you for your keynote address?
Thank you very much. It is very difficult to speak in the last session and being the last but one speaker. So before that, I just wanted to have a request to all of you to have a big clap for NIT Patna, Wetland and Professor Jha. Because of him, we all are together here and we are rejuvenating our own energy in the last session. Basically, Wetland Water Resources for Sustainable Development, that is the title. And sustainable development is output and water resources is input. As per the topic for the conference, water resources is input and sustainable development is output. For achieving this